When you load thousands of tons of heavy cargo onto a ship, two physical reactions happen at the exact same time. The entire hull sinks deeper into the water, and the ship tilts toward the added weight. If you miscalculate this dual reaction, you can push the bow too deep into the water, or raise the stern so high that the propeller is exposed. Accurately predicting the final position of your ship before a single container is loaded is the most challenging requirement of ship stability. While the physics of sinking and tipping happen simultaneously, the math does not have to. To make this calculation solvable, we use the sink and tilt method. We freeze time and break the reaction into two distinct steps: a uniform downward sinkage followed by a longitudinal tilt. To calculate this, you need 5 specific pieces of data about your vessel: your initial drafts, the tons per centimeter of sinkage, or TPC, the moment required to change your trim, or MCTC, the total ship length, and the exact location of the center of flotation. To understand the logic here, you need to picture your ship as a giant seesaw. The center of flotation, often labeled LCF or F, is the exact pivot point or fulcrum of that seesaw. First, loading cargo directly on pivot point F creates no leverage, so the ship sinks uniformly. Second, sliding that weight forward away from the pivot creates the leverage necessary to tip the hull. By pretending the physics happens in these two distinct steps, calculate the sink, then calculate the tilt, we isolate our variables and clear a straightforward path through the math. In this example, we load a 450-ton weight onto a 90-meter ship. To calculate the uniform sinkage, we divide the total cargo weight by the ship's TPC of 10. Dividing 450 tons by 10 gives us 0.45 meters. Because this first step represents the whole ship sinking evenly into the water, you will add this 0.45 meter value to both the initial forward draft and the initial aft draft. Now we calculate the second reaction, the tilt. We do this by finding the trimming moment, which is a measurement of the mechanical tipping force we created when we slit the weight away from the pivot point. In step 3, calculate the moment by multiplying the 450-ton weight by its 15.5-meter distance from the LCF, generating 6,975 ton-meters. Then divide that tipping force by the ship's MCTC of 120, resulting in a 58.125 centimeter total trim. That 58 centimeter number represents the total end-to-end change of trim, but this is the sum total of the tilt. It is not the individual draft change for the bow or the stern yet. Here is where many calculations fail. It is a common mistake to assume the pivot point sits perfectly in the center of the ship and simply divide that total trim evenly by 2. In reality, a ship's pivot point is almost always off-center, and mechanically, the end of the lever that is further away from the pivot point will always swing through a greater vertical distance. In step 5, we split the trim. Calculate the forward change by multiplying the total trim by the pivot to bow distance divided by the ship's length, giving 0.303 meters. Repeat this for the aft draft using the pivot to stern distance to yield 0.281 meters. You can always verify your math here. If you add these two split numbers back together, they will perfectly equal your total calculated trim from the previous step. Now we execute the final accounting phase. We stack our 3 components, the initial drafts, the uniform sinkage, and the split trim, into a single table. Looking at this final table, we build our foundation. We list the starting forward and aft drafts, and then add that 0.45 meter parallel sinkage uniformly to both columns. Before we add the split trim, we must assign our positive and negative signs. Because we loaded the weight toward the forward end of the ship, the bow will go down, so we add draft there. The stern will rise up, so we subtract draft there. We slot in our split calculations: plus 0.303 on the forward side, minus 0.281 on the aft side. Add the columns vertically, and you reveal your exact final forward and aft drafts. Visualizing exactly which way the seesaw is tipping in your head is your ultimate safeguard against accidentally adding when you should be subtracting. That is the complete process. Calculate the uniform sinkage, determine the tipping force, split that tilt proportionally based on the pivot point, and combine the results. What starts as abstract math on a page translates directly into the physical, safe resting state of the hull. If you are loading multiple weights at once, you run this exact same workflow. You simply consolidate your weights into a single final cargo number and sum your individual forces into one final moment before starting the math. By utilizing the sink and tilt method, you prove exactly how the water will react to your cargo plan, guaranteeing the vessel remains balanced and safe before a single crane is even fired up.